Welcome to today's tutorial. Let's get started. Let's have a look at our agenda for today. Today we are looking at retrofitting legacy OCS. We'll start with a brief history of the first Horner OCS all-in-one controllers that were text-based units. Then we'll go through the retrofit procedure that we recommend when you're taking older controls from Horner and replacing them with newer features. We'll have demonstrations throughout, and as always we'll finish with a Q&A session. First we'll look at a brief history of the first Horner OCS controllers. The first all-in-one controllers were released back in 1998. They were text-based as microprocessors then did not provide the type of performance for both fast logic scan rates as well as responsive user interface for a pixel-based display. Competing products with graphic units at the time were underpowered with very long scan rates. Horner felt it was important to provide a fast scan rate with these controllers. These text-based units were available with a 2-line display or a 4-line display, and there were different varieties of memory, including units with 2048 R-type registers and some later units that had up to 10,000 of those word-type registers. These units were based on an Intel microprocessor. Intel at the time were a big player in embedded microprocessors. These units used a parallel backplane, which were better at the time than serial backplanes, which were common, but they had worse performance. Today, of course, with modern architectures, automation-related networks are serial in nature. These units were all metal in construction, as tooling of plastic back at that time was very expensive. This made it a very rugged product, though not the most elegant. Now let's talk about the I/O element of these older OCSs. I/O was primarily modular at the time. You could have up to 4 smart stack modules on the back of every unit. There were more than 20 different I/O modules available in the family, and if you wanted Ethernet, you did have to add a special Ethernet module in the first slot to support that. They also had a single RS-232 port that was used for both communications as well as programming. So now let's look at the recommended retrofit procedure. So what we're talking about with retrofits is taking machines running these products and putting newer Horner controls on them. So the first step is to get a copy of the CSP file or Cscape program which you'll need for this retrofit process. If you don't have a copy, you should upload the program from an existing unit, provided that the program is still in there. If you're going to upload the program, we don't recommend that you start with the latest version of Cscape, but instead go onto the Horner website under support and then Cscape, and from that page you can scroll down to the Cscape archives link. Here you'll find older legacy versions of Cscape. The version we recommend that you start with is Cscape 8.52b, which is the best version for compatibility with the original OCS100 and 200. If you attempt to upload and it tells you that the program was developed using a newer version than 8.52b, then we suggest you download version 8.8. That's probably the last viable version of Cscape where the OCS100 and 200 were our mainstream products. You also need to have the right cable to connect to your old OCS. If you're currently a user of our standard OCS cable kit, then you're almost there, as the USB serial adapter that's included with our standard cable kit is pinned out properly, but it doesn't plug in because of a mechanical interference. So there you need to add a 9-pin male to 9-pin female straight through adapter or something like that. If you can't find that anywhere, we also have a dedicated kit which is effectively a USB to serial adapter along with the right cable that's available as an HE500 USB 600. You can use that part number to make the connection between your modern computer and these older units. If you're attempting to do the upload and that program happens to be password protected, first you should ask yourself, does your company own the rights to this program, or does the original OEM machine builder own the rights to the program? If you do own the rights to the program but you don't have the password, then you need to contact the Horner Tech Support Department, and we will start the due diligence process to make sure that if we do move forward and help you get the program, that we're not violating anybody's intellectual property. Once we have that program, the first thing we'll do is make a copy of that file that we'll work on. Then we'll start examining that program in Cscape. First, we'll open up that program in an older version like 8.52b or 8.8 and take a look at a few things. Then we'll get to the point where we'll open it up in a newer version of Cscape. We'll start by analysing the I/O requirements. I/O requirements are a big part of any retrofit because that's a potential area where differences could be found and you're likely going to be replacing that with a newer I/O system. So we need to know precisely what I/O is being used with the original system. We'll start in the hardware configuration and then look at what I/O has been configured with the original system. We'll look at the part numbers for each of those modules as well as the memory addresses that have been assigned to each of those modules that are plugged into this older OCS. To make sure we do an effective job on a retrofit, it's important that we get as much information as possible about the original I/O module. For that, go to the Horner website and then to our documentation search page and find the cut sheets for the I/O modules that are used on the system. That'll give you information on the specifications, current ratings, voltage ratings, etc. If for whatever reason you can't find the document on our website, if all else fails, just Google it with that part number information and you'll likely find what you're looking for. Another thing to note here is that just because a module is plugged in that supports a certain amount of I/O, it does not mean that every I/O point is being utilized by that existing system. For example, there might be 40 or 50 I/O points plugged in, but you may be using a fraction of those. So why replace all that I/O if it's just going to sit there being unused? To see what's actually being used, you can look at the real-world I/O addresses assigned to each of these modules that are plugged in. Then you can go to the element usage table. That's a tool within Cscape that's accessible from the program menu that allows you to scroll through and find reference by reference what's actually being used in the program. Finally, there's the Cscan I/O tab to look at. Some of the older models that were built expanded the I/O beyond what was plugged into the back. So if you find SmartSticks I/O on there, for example, then that can be continued to be used. However, for any remote SmartStack I/O, all used I/O points will need to be replaced because those products are obsolete. In those cases, you'll want to go back and find the memory addresses assigned to those particular modules. The final step of the I/O analysis is writing down a list of all the I/O that you'll utilize moving forward and effectively replacing it with new hardware and getting the addresses put into the new system. Using a spreadsheet is handy for this. Here we recommend that you use a spreadsheet and you can see an example of that on the screen. Now let's demonstrate that process in Cscape. Here is a program that was developed for a machine that utilized the OCS200 for doing some filling. I'll begin by pulling up the hardware configuration and you can see here is the OCS200 controller. I'll go under the local I/O tab. Here's the modules that were plugged into this legacy system. This is a high-speed counter. Keep in mind, high-speed counters are a bit different. They have a lot of I's, Q's, AI's and AQ's that are allocated to them, even though those don't all represent physical inputs and outputs. So again, this is a high-speed counter module, but this is all the different real-world I/O memory addresses that are allocated to it. The second module is a 16-point DC output card. That's the only two modules in this system. Now let's look at the module setup. For the high-speed counter, we have two 16-bit encoders that are plugged into the high-speed counter module. They are using some built-in physical outputs on the high-speed counter to directly fire those based on encoder position. So that is the I's, Q's, AI's and AQ's that are assigned to those modules. But how many of those are actually being used? To find that out, I'll go into the element usage option and start looking for real-world I/O references. What you'll find is we're just using a few AI references for the encoder accumulators. We don't find any I registers at all, and of course we'll have high-speed counting we'll have to take care of. If I scroll down, you'll see we do have some %Q outputs, and if we count those up, we have 12 digital outputs that we need to support moving forward. Next, we need to select a replacement model OCS. You have a lot of choice here, from a micro OCS unit to an XL series unit, or maybe an XLE or an XLT. Here you need to ask yourself what size screen you want and what are your I/O needs. If you're not sure, a good default option is the EXLW. It's a great default choice for a couple of reasons. First, it's physically around the same size as the OCS100 and the OCS200. If you have an enclosure that's been sized for those products, the EXLW will fit quite well. It has a 7-inch or 800 by 480 screen, and it has a lot of I/O options available as part of the XL series. In my case, I'll use the EXLW Model 3. So what if the list of I/O I came up with exceeded the I/O that's available directly in one of the OCS models? In that case, you can simply add additional I/O to the system through one of our expansion I/O families, whether that's Smart Rail, Smart Block, Smart Sticks, or whatever the case may be. If you have AC inputs, we have an opto-isolator accessory that mounts on the DIN rail that can convert those AC input signals over to DC so they can be used with a modern OCS. The next step in our retrofitting process is to look at the user interface as it was implemented with the existing machine. These original products were text-based units and had a very simple user interface made up of screens with text fields, data fields for displaying data to the operator, as well as menu screens and alarm screens. A menu screen option would allow a user to implement a simple menu to navigate from screen to screen and set parameters, etc. Alarm screens were screens that would only be displayed if they were forced by the ladder, and those were typically used to display diagnostics. Things we need to note from our user interface are any data fields that are included on any of the screens, because they may contain important variable information that the user needs to know. The editable ones may also need to be adjusted at runtime, so we want to make a note of those as well. We'll also look for any force D coils in our logic as shown in the bottom right. Those were typically used to enunciate alarm conditions by forcing a particular screen to be displayed in a certain machine condition. That will give us clues in terms of how many alarms were enunciated with this older machine. The last thing we'll look for in the user interface is any K contacts, indicating the use of one of the function keys. For any function keys that were used as jump buttons, or even the ones that were used as operator inputs, you'll likely want to replace those with buttons on the touchscreen on your modern unit. Now let's go back to Cscape and look at the user interface changes. I'll click on the screen editor icon, and here instead of the graphics editor coming up, we have this text display for the first screen, number 1. On that we have descriptive text, data fields, and there is an R at the beginning of each of these data fields which indicates that they're read-only. If we double click on that data field, we can see which register is tied to it, what format it's in, and how many digits it has, or whether it's editable or not. We also have this screen button which allows us to navigate through my screens. For these screens that have alarm screen checked, that means the only way for these screens to come up is if they're forced by the ladder. And then some screens are not alarm screens, so they can be navigated to with the arrow keys. So this is the sort of information we're looking for as we're examining the user interface programming, understanding what data fields are important to the operator, and how the navigation was done in this original system. The next step in the retrofit process is logic changes. Instead of starting over again, we'll take advantage of that original logic. The first thing we have to do is some remapping, because the SmartStack I/O mapping points will probably not match up in a one-to-one manner with the addresses for the replacement system. I'll pull up that list of I/O that I made in an earlier step, and I'll add a column for the new addresses. So now I've documented what the old memory address locations are and what the new ones are going to be. Next, we'll open up a copy of our program in a new version of Cscape starting at 9.9 and start the process of finding and replacing the old memory addresses with the new memory addresses. Then you can use the I/O names tool or Excel or a spreadsheet program to fix the I/O names and get those remapped as well, because just doing a find and replace will not change both the program coils as well as the I/O name. Let's demonstrate this now in Cscape. So I have opened the old program up in a new version of Cscape. So then I'll go into Edit and then the Replace option. I'm going to look for my old memory addresses starting with Q41. My new address I need to replace that with is Q1. we always want this start from the top box checked, and then I'll do a replace all. It comes back and tells me 4 occurrences have been replaced. I'll check that address off my list that I've made, and then I'll go back one by one, replacing all the old addresses with their new addresses. Make sure you save before you start this process in case you need to go back a version and retry. The next thing I need to do once that's all complete is to fix the IO names. I can do this either directly in the IO names or from Excel. So I'll find Q41 and I'll change the IO name to Q1. Then I'll simply do the same for the rest of these addresses that I did my search and replace on. The next step is to go through the logic and make sure we understand how our program works. Here we're looking out for anything that's going to have to change substantially. For high-speed counting, for example, you'll want to make sure that same logic will work with the newer high-speed counter. You should also look at a user interface type logic and decide if it's still relevant. For example, you may want to use jump buttons to navigate instead of function keys, or you may want to use the alarm function in the graphics editor instead of forcing the screens to display diagnostics. Now I'll quickly demonstrate in Cscape some things that I might want to change. Starting at the beginning of my program, what am I looking for in my logic that might need to be changed? Here are a few rungs that have to do with forcing a certain screen to come up. In this case, we want to display the screen whenever function key 7 is pressed. So I have to decide here if I want to keep this sort of user interface or am I going to get rid of that. As I scroll down, here is some more logic that's forcing particular messages, and that's walking the user through the setup procedure for the machine to start. So that is something I'll have to either utilize as it is or just replace. So that is an example of some of the decisions that we'll have to make. For this program, however, the majority of the logic will remain because it's mostly about machine sequencing, which doesn't really change. Next, let's talk more about the user interface design. Remember, in a previous step, we went through and examined and noted the current user interface implementation to get an idea of what variables were accessed, which ones need to be changeable, etc. From this, you can design the user interface as is appropriate. Now I'll demonstrate some of the decisions we made when making a more modern user interface for this machine. So here is my user interface. Here, for this retrofit, we designed something simple that could be done quickly to get the retrofit back up and running as soon as possible. So now I'll show you this using my navigation tool. Instead of function keys, we ended up with dedicated buttons for jumping to different screens, such as to home, to an encoder display, to the current count, the cycle count, etc. Those are all functions from the previous implementation, but it used arrow keys to navigate to those screens. Then from a setup standpoint, we have arrow keys to jump them through the setup process for all the different parts of the machine that need to be set up initially. You can see when I go to the matrix view, these are all the screens that we ended up replacing. There are less screens here with the retrofit because I also implemented the alarm handler in the new EXLW, so a lot of those alarm type screens were eliminated because they weren't needed. Now let's look quickly at what the user interface looks like at runtime with the EXLW that I have here. First, I'll show you how the navigation was done on the OCS200. For this, we just navigate using the arrow keys, and I can move between my different screens. This is a very basic type of navigation, and we can also use the function keys. For example, when you press function key 7, it moves you to a different screen. So here's my EXLW. Of course, we don't have any I/O that's actually updating here because I just loaded the program, but I just want to show you the navigation. So here we can go to the main screens using the jump buttons, and then we can walk through the setup process with these arrows navigating from setup screen to setup screen. That concludes our demonstration for today. Thank you for joining us for today's tutorial, and the Q&A session will begin shortly.
Okay, folks, so that's the part one of this pair of webinars on retrofitting legacy OCS, and part 2 will come along in next week's slot, 1st of September. So I've got up on screen there the upcoming webinars. So there's today's and the part 2 shown for next week. We've then got the X5, a truly unique all-in-one controller, followed by OCS in a 12-volt DC environment. So we're looking at hooking things up to machinery or vehicles. Often there's only 12 volts available. And then the week after that, we're looking at using the XLE-E as remote I/O. So that will be putting the Ethernet-based XLE onto a Ethernet network and using that as remote I/O for another device, another OCS. So they're the upcoming webinars. We hope to see you on those also. Thanks very much for signing in today, and hopefully we'll see you all next week. Thank you very much.